The priority methods we have looked at so far assign priority to packets based on packet attributes. In our case, we have matched on destination subnet. The two methods we examine next, ccnp priority and PIPQ, give priority to PVCs rather than to packets. In the ccnp priority method, a priority list is used to associate traffic with a priority level, high, medium, normal, or low. You then use the priority ccnp group command to associate a priority level with a PVC. We will use the same priority list we have been using, which puts traffic destined to subnet 112 in the high queue and traffic destined to subnet 113 in the medium queue. Normal and low priority traffic will also go over ccnp 113. To demonstrate this feature, we will add another PVC on S0 of FRS. Note that if traffic comes into FRS on S00 on either ccnp 112 or ccnp 113, it will be mapped to serial 1 ccnp 112, which is connected to R2. Our new PVC is inactive because it is not configured on R1. First, we go back to R1 and remove the LLQ configuration. Since ccnp priority uses the interface queue, we can remove the traffic shaping commands. We then add the priority ccnp group command. First, we remove the traffic shaping. Then we remove the map class from ccnp 112 and enter the priority ccnp group command. This command references the PVCs in order of priority, high, medium, and low. In order to make the priorities effective, we need to add the priority group command to the physical interface. Before we examine the operation of ccnp priority, let's go over to R2 and see if it's working. We'll simply recall our show policy map interface command. Note that as required, the traffic to subnet 112 is coming through at the full 40K rate, but the traffic to subnet 113 is being dropped back to about 23 or 24K to accommodate our 64K clock rate. Back on R1, let's see how ccnp priority handles two PVCs on a single point-to-point subinterface. First, we'll take a look at the configuration on interface S00.2. Notice that the primary ccnp is 112, referenced by the frame relay interface ccnp command. However, our frame relay priority ccnp group command also references ccnp 113. Let's compare this to our frame relay map. Here you see the primary ccnp, ccnp 112, associated with the point-to-point subinterface, but 113 is also noted. Anything that goes into the medium, normal, or low queues is associated with ccnp 113. As you can see, this feature allows us to have multiple ccnps associated with a point-to-point interface. The mapping is taken care of by the priority queuing. On the interface, we see our four queues, high, medium, normal, and low. The high queue shows no drops. There's only one packet in the queue. The medium queue is full, 40 packets in a 40-packet queue, and has dropped over 800 packets. We can demonstrate that the traffic in the medium queue is actually taking ccnp 113 by examining the debug output of both frame packets and priority. First, we'll turn on debug frame packet and then debug priority and clear the log. Note that priority queuing shows a packet destined to 113-100 going into the medium queue. We then see a packet going out on ccnp 113. CDP, or Cisco Discovery Protocol, is not explicitly classified by our priority list, so it should be in the normal queue and go out ccnp 113. Let's test the log for that. simply do a show log pipe begin CDP. Here you see CDP packets being prioritized into the default normal queue, then exiting the subinterface on del-C 113. Del-C priority levels are useful when you have multiple parallel PVCs on the same interface and want to prioritize traffic. On some Cisco frame relay switches, the provider can prioritize traffic within its frame relay cloud based on the del-C it receives the traffic on. Like del-C priority, PVC interface priority queuing, or PIPQ, assigns a priority per PVC rather than per packet. Unlike del-C priority, it can be used when PVCs are on different subinterfaces. Priority lists are not used in PIPQ, so one of the challenges with PIPQ is getting particular types of traffic associated with the right PVC. We have reconfigured our lab so that there are now two subnets on different PVCs connecting R1 and R2. We have configured static routes so that the traffic to subnet 112 has a next hop of 12.2, and the traffic to subnet 113 has a next hop of 13.2. Now traffic to subnet 112 will take PVC 112, and traffic to subnet 113 will take PVC 113. We can verify this with a simple trace route. We have temporarily shut F00 to relieve the congestion. Let's try a trace route to 112.100. Here you see that the next hop to that subnet is 12.2. Now we'll try the same thing to subnet 113. And the next hop to subnet 113 is now 13.2. We will want the high priority traffic to be the traffic that leaves R1 on del-C 112 and the lower priority traffic to leave on del-C 113. First, let's no-shut F00 to get our traffic flows back. The first step in configuring PIPQ is to create a map class for each PVC and specify a priority level, high, medium, normal, or low, for the map class. We'll create a map class called PVC 112 and associate priority of high with it, and then create another map class called PVC 113 and assign a medium priority. Next, we apply each map class to the appropriate PVC. We can go to the interface, reference each del-C, and then reference the appropriate class. Finally, we activate PIPQ on the physical interface with the interface queue priority command. We'll clear our counters, clear our log, and then start debugging priority. Let's go over to R2 and see if we are getting the expected traffic counts. We'll simply recall our show policy map interface command. As expected, all 40K of the traffic to subnet 112 is arriving, but the traffic to subnet 113 is being cut back to about 23 or 24K. Let's investigate the operation of PIPQ on R1. First, we'll examine the interface queues. Note that the queuing strategy is called del-C priority. Apparently the code writers consider PIPQ a kind of del-C priority. Note our four queues, high, medium, normal, and low. The high queue has no drops. The medium queue is just about full and has had over 300 drops. Let's verify what's getting dropped by looking at our debug output. Simply filter on the word drop And notice that it's all del C113 traffic in the medium queue that's getting dropped. So our medium queue is associated with del C113. At the moment, our 64K pipe to R2 is completely full with user traffic. If we removed our current priority queuing scheme, routing protocol traffic on both PVCs would likely be discarded. Cisco IOS provides a special broadcast queue on frame relay interfaces that can be used to protect and police traffic sent to broadcast and multicast addresses. To demonstrate the broadcast queue, we will shut the traffic from the generator and remove our current queuing. And finally, we'll clear the counters. We have enabled RIP version 2 on R2. This allows us to ping 224.0.0.9 multicast address from R1 and get responses from R2. Let's give that a try. This is the multicast address for RIP version 2, and hopefully R2 will respond. Notice that we get responses on both 12.2 and 13.2. Let's take a look at the default broadcast queue on S00. We'll do a show interface S00. Note that the number of broadcasts sent and dropped is being tracked. When a broadcast is sent on a frame relay interface, it is duplicated and sent out each PVC configured for broadcast. Here, one copy was sent out PVC 112, another copy was sent out PVC 113, even though we only sent one ping. Let's see what happens when we send 100 of these pings at a high rate of speed. First, we'll clear the counters and do a ping with repeat count of 100 and a timeout of 0. Notice that, of course, we got no return. What we really want was some counts to see what was happening with the queue. Notice that the broadcast queue is empty. Only 77 were sent, 124 were dropped. It shows 200 pings were sent, counting each multicast once for each PVC on the interface. To configure the broadcast queue, you enter the size of the queue in packets, the maximum rate in bytes per second, and the maximum rate in packets per second. The effective maximum rate is the lower of the maximum byte count or packet count. We will configure the broadcast queue for a depth of 200 packets, a byte limit of 1500 bytes per second, and a packet limit of 1 per second. We'll clear the counters. Now let's repeat our high rate ping of 100 packets. And now we'll check our broadcast queue. Notice the multicast pings are now being saved up in the broadcast queue. There are 190 now. Every second, another multicast ping is taken out of the queue and sent. You see the queue size is now down to 177 packets.